So one concept I want to share, although I have shared in lecture class also, but just as a part of revision, so that when we are attempting the numericals on these concept, it is easy to you. I have told you that when there is no load connected, still in the primary side current flows. Okay, so that current is called no load current, although its percentage in comparison to full load current is very small. You can say hardly 2 to 5%. Okay, so what is the role of this exciting current or no load current? It is having two purpose. First, as the name suggests, exciting current or no load current, it excites the transformer core to prevent it in going to the saturation. Okay, current is passed, so a part of the current is passed or used, and as you know, flux is directly proportional to current. So flux is produced and magnetic flux density is produced, a magnetic field is produced, so the core does not go to saturation. Okay, and the second component of this no load current is used to overcome the losses which have occurred in the core, or you can say to compensate the core loss. Okay, so for our convenience, it is always assumed that the current is lagging based on the fact that the maximum current is based on inductive load. Okay, so if this is the voltage of the transformer, applied voltage, you can say it is RMS in nature. Okay, so the current is lagging. Say this is the current which is lagging, although the values which are given, it can be instantaneous value, RMS, whatever it may be, but when we are drawing the phasor diagram, it is represented by phasor quantities. Okay, so this current is calculated, say it is lagging by 60 degrees. It is also, I have taken 60 degrees because it is part of our next numerical. Okay, so let us do the numerical as well as this concept simultaneously. So the supply voltage is, say, 200 sine omega t. Okay, omega t or 314 t, it is all the same, it's okay. So this 200 is our maximum value. So when we divide it by √2, we get the RMS value. Okay, and the current is given as 3 sine omega t minus 60. Okay, so this is the instantaneous current. Maximum current is 3, so the RMS current is 3√2 and the small I becomes capital I. So this current is lagging the voltage by 60 degrees. Okay, now if we are required to determine the core loss and the parameters of the no load circuit, what we have to do, this is the no load current and it is also represented by 0 subscript. 0 is no load, 0 all the same. Okay, So what is the core loss? I have mentioned this in the single phase as well as in the three phase systems, that if the power loss is not defined or asked that which power loss we are talking of, then we have to take the average power loss or average power in all the cases. Okay, so average power of the single phase, again, since we are discussing the transformer, and if the number of phase, whether it is a single phase transformer or three phase transformer, if it is not defined that which transformer we are talking of, then always take single phase transformer. Okay, so what is the value of the power, average power in single phase? It is vi cos phi. So v is 200 upon root 2, I naught is 3 upon root 2, just we have calculated, and cos 60. We will calculate this and get the value of the power loss. Earlier we are talking of power, but since the current here is I naught, so we are talking here of the core loss or power loss, which is calculated in watt. Okay, so this is the core loss. Now, since I have mentioned you that this no load current is having two component, one is the energy loss component and other is the magnetizing current component. Okay, so magnetizing component is on the x-axis, it is Im, and this is IE. So what is IE? It is I naught cos phi naught. If this is I naught cos 60. So if this is I naught cos 60, then it is Im sin 60. You can calculate this way, or if this IE is known to you and this is known to you, you can apply the Pythagoras theorem to calculate the Im. Both ways it is correct. Okay, clear? Now the no load resistance and no load reactance components, these are the parameters of the primary side which are to be calculated. We can draw the equivalent diagram like this. Suppose this is the V1, which is the applied voltage, and so this current is coming here, and this I naught current is coming here, and it is divided in two parts. No load resistance part. This no load resistance part is corresponding to the energy loss component, and this magnetizing component is responsible for the excitation of the transformer core. Okay, so this resistance is denoted as R naught, and this is denoted as X naught. Okay, so now since we know the voltage and the current, so by applying the Ohm's law, we will calculate this no load resistance and no load reactance. So this R naught is V upon IE. V is known to us 200 upon root 2. IE is just we have calculated. We will use this to calculate the R naught in ohms. Similarly, X naught is calculated as V upon IM. IM we have just calculated. V is 200 upon root 2. We substitute these values to get the result. Okay. So this was the numerical which we have just discussed. So everyone can see this, that this voltage 200 sine 314t is applied to the transformer winding in the no load test, and the current was found to be 3 sine 314 minus 60 degrees. Determine the core loss and its parameter. So first of all, we have calculated the RMS current by knowing the maximum current. So this RMS current is the no load current which is flowing, and the core loss, total core loss is VI cos phi in the single phase transformer. So this core loss VI naught cos naught, it is calculated. The RMS value of the voltage is 200 upon root 2 from the instantaneous value of the voltage which is given. Okay. Now the two components are the energy loss component, which is the I naught cos phi naught. Okay. And this is based on the assumption that the angle phi naught, which is being discussed here, is the angle between the current and the voltage while current is lagging. Okay. But if this I naught, sorry, this phi naught is taken as the angle between the x-axis and the current, then the cos phi becomes sin phi and the sin phi become cos phi. Okay. So you should not just mug up. You should know the components of the current where they are positioned. Okay. Magnetizing component of the current is positioned in the x-axis, and core loss component or the energy loss component is present in the y-axis. Okay. So once we are this IE is known to us, we can calculate the IM using Pythagoras theorem, or you can also use I naught sine phi naught. Both are good enough. Once you know the phi naught is 60 degree, then sine phi naught you can also apply. There is no problem. Now the no load resistance R naught is V upon IE, and this X naught is V upon IM. Okay. So a 100 kVA 2400 upon 240 volts single phase transformer has the exciting current of 0.64 amperes and core loss 700 watt. High voltage side is energized. Okay, so calculate the components of the no load current and its branch parameter, same as the previous one. So first of all, since I naught is given as 0.64 amperes, I naught cos phi naught is to be calculated energy loss. So iron loss is given here. Okay. So VI cos phi is given already. Okay. So this iron loss is given as 700. V1 is given 2400. We will divide these two components to get the I naught cos phi naught, which is the iron loss component or the energy loss component. This is actually energy loss component. It is also mentioned as iron loss component. Okay, because it is responsible for the to compensate the energy loss due to hysteresis loss and eddy current losses, and these eddy current losses and eddy current losses and hysteresis losses occur in the iron. So it is also called iron loss current. Okay. So next is the IM. It is, you can use the Pythagoras theorem. No load branch parameter R naught and X naught is calculated in kilo ohms. Now in this question, no load current of a transformer is 4 amperes at 0.25 power factor. Okay, so there are different methods of representing and giving the data. When the power factor is given, it means that the cos phi is given. Okay, or more precisely, cos phi naught is given. Okay, when it is supplied by 250 volts, it is the primary side, and number of turns of the primary side is given. Calculate the flux, core loss, and magnetizing current. First of all, we will apply the EMF formula. E1 is equal to 4.44 F N1. Number of turns is given to us. EMF is given to us. Flux can be calculated. Okay. Now the core loss is V1 I naught cos phi naught. V1 is 250. I naught is given as 4. Power factor is given. So power loss is calculated. Now Im is I naught sin phi naught, which is I naught sin theta is 1 minus cos square theta. Same formula is applied to get the Im. So in this question, we have to calculate the voltage regulation of the single phase transformer, in which ohmic drop is 1% and the reactance drop is 5% of the voltage at the following power factors. Power factor is given as 0.8 lagging and 0.8 leading. Okay, so this question is a bit different from others. It is based on the knowledge of our voltage regulation. Okay, so what is the per unit resistance? Per unit resistance is the when you calculate by dividing its value by 100. So 1% and 5% is given as ohmic drop and the reactance drop. So it is divided by 100 to get the per unit resistance. So the percentage voltage regulation formula is per unit resistance into cos phi plus per unit reactance into sin phi into 100. It is calculated as 3.8%. So now when the power factor is leading, when we have calculated the derivation of this voltage regulation, I have emphasized that when the power factor is lagging or we are having the inductive load or RL load, then the voltage regulation is calculated using the plus sign between the drops of the resistance and reactance. But if our power factor is leading or we are having the capacitive drop, capacitive reactance or capacitor in the load or in the drop, I should say, not in the load, in the drop, okay, then there is minus sign between the drops between the resistance and reactance. Okay, so same will be reflected here. So when the power factor is 0.8 leading, so sin phi becomes minus 0.6. Okay, cos phi remains positive because cos of minus theta is equal to cos of theta. But when the phi angle is here, we have taken while calculating the derivation that the phi angle is the angle between the current and the voltage when the inductive load is calculated, and it is taken as positive. But in case of capacitive drop, current is leading. So when current is leading, the polarity of the angle changes. So the plus phi becomes minus phi. Okay. In the cos phi terms, cos phi is equal to cos of minus phi. It is not affecting. But When the sine phi becomes sine minus phi, it becomes minus sine phi. Okay. So this is the reason for the change of the sign as well. Okay. So now the percentage voltage regulation is the per unit resistance into cos phi plus per unit reactance into sin phi. Sin phi is calculated as minus 0.6. So it is substituted here to get the minus 2.2 percentage of voltage regulation. So in this numerical, we are having 25 kVA transformer, and the iron losses and full load copper losses are given. Okay. Iron losses is given as 350 watt, which is fixed, and copper loss is full load copper loss. It is given as 400 watt. Calculate the efficiency at full load unity power factor and half load 0.8 power factor. Okay. So at full load and unity power factor, the P, which is in the numerator or the output, so it is the rated kVA into power factor. So rated kVA is our 25 kVA and unity power factor is given. So it becomes 25 kilowatt. And again, this thing is to be kept in mind that while we are calculating the efficiency, the units in the numerator and the denominator should be same. Okay. That's why if it is calculated in watts, okay, then the losses should also be in watt. But if the numerator is in kilowatt, then the denominator losses should also be calculated in kilowatt. If it is given in watts, divide by 1000. Okay. So while we are dividing by 1000, this 350 watt become 0.35 watt, and this 400 watt will become 0.4 kilowatt. Okay. So efficiency is output upon input. So output is 25 and input is output plus losses, 25 plus 0.35 plus 0.4 into 100, and it is calculated as 97.08%. Now we have to calculate the efficiency at half of the full load and 0.8 power factor. If the power factor is given, lagging or leading, it is good enough. If it is not given, you are required to take as lagging. Okay. So now the numerator part or the output transformer output is, or you can say single phase transformer is, so VI cos phi is there. So voltage, there is no change in voltage, but the secondary side current is reduced by half. Load is reduced by half. That means secondary side current is reduced by half. So 1/2 into rated kVA into power factor. So what is power factor? Power factor is 0.8 lagging. So it is calculated as 10 kilowatt. Okay. Iron loss remains same as 0.35 kilowatt, and the copper loss, which is dependent upon the current. So I square R loss. So current is reduced by half. Okay. So copper loss will also reduced by 1/4 or I square parameter. Okay. So 1/2 square into 0.4, we get 0.1 kilowatt. So when these revised values are substituted, we get the efficiency as 95.69. So in this numerical, 50 kVA transformer is given. 11 kV upon 400 volt is the voltage ratio. Voltage ratio, not voltage transformation ratio. Iron loss and copper losses are given. So in this question, it is not given that 600 watt is full load copper loss, but here there is a word of caution. Whenever full load copper loss is not given, still you have to take it as full load only. Okay, if it is specified, it is good enough. Otherwise, you have to take full load only, because in the next line it is given as rated conditions. So that means the same. Now we have to calculate the efficiency on unity power factor at full load and load for maximum efficiency and losses. Okay, so first of all, we will again calculate this losses which are given in watts to the kilowatts. Output P is rated kVA into power factor. Power factor is given as unity. So 50 kVA becomes 50 kilowatt. So efficiency is calculated by substituting these values. 50 upon 50 plus 0.5, 0.6. It is calculated as 97.85. So now we have to calculate the transformer for maximum efficiency. So we have derived that at maximum efficiency, iron losses and copper losses are equal. So what is copper loss? It is X square PC. Okay, where X is the fraction of the load, full load current which is being drawn. Okay, so X is under root of Pi upon PC. So it is calculated as 0.91. So if the full load current is say 100 ampere, then maximum efficiency will occur at 91.29 amperes. Okay. So what is the load corresponding to maximum efficiency? X into rated kVA. Rated kVA is 50. So it is calculated as 45.645 kVA. And the losses at the maximum efficiency, iron loss is equal to copper loss. So the copper loss will also become 500 watt.